So, in our previous couple of short lectures about cosmology, we talked about how uh, they started going from thinking that the universe was always static to realizing that it wasn't. And it was all based on the observations of the nebulae that were out there, what they called the spiral nebulae, which they realized eventually were galaxies. When Hubble discovered they were galaxies, it sort of set everything on its ear in terms of how they thought the universe was. Uh, Prior to Hubble's discovery, or about the time of Hubble's discovery as to what these things were, uh, 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 Alexander Friedman had worked through the mathematics of Einstein's field equations, applying them to the universe as a whole, and realized that you come up with a set of solutions for the universe that involve a universe that is not static. The universe either expands or it contracts. No static universe. Albert Einstein couldn't accept that, and we talked about how he inserted an extra term into the equation here, a cosmological constant, to make for a static universe. Took that out shortly after Edwin Hubble had discovered that the universe, in fact, was not static. The farther away something is, the faster it's moving away from us. That's exactly what you would expect if Friedman's equation is solved for an expanding universe. And so Einstein, realized, well, maybe the universe is not static. Maybe it is expanding. And then Hubble gets credit for this. But even though Hubble got credit for the discovery, Georges Lemaitre, Monsignor Georges Lemaitre, had just a couple years prior to Hubble's publication of his work, published his own findings showing that the universe was expanding. And he came to the same conclusion, that the universe was expanding, and he came to the conclusion again from measuring and analyzing the recessional velocity of these spiral nebulae. And realizing, once Hubble had discovered, that these were galaxies, that this would in fact mean an expanding universe. And so that he just a couple years prior had published the same sort of thing. And both of these, Lemaitre and Hubble's work, were in fact based on Festo Slipher's work, who actually started the whole process and rarely gets the credit due for discovering that. Well, Lemaitre, even though he and Hubble had come up with the same basic idea, never really, throughout most of the 20th century, never got the recognition he probably deserved. And part of it was that he made a mistake right away, proposing the primordial atom, that if the universe is expanding, it all running backwards was in one spot, and a big ball of stuff which somehow blew into space, creating blobs of stuff going away outwards, which we now see. Now, that turns out that doesn't even remotely describe what you would see. Because while, yeah, you're out here on one of these blobs that becomes a galaxy and the other things are getting farther away, you don't necessarily see the ones that are farther going away from you that much faster than the ones that are up close. So it doesn't exactly reproduce the observations. Also, if everything was crammed into a big ball here, then gravity would actually make it collapse into a black hole instead of blowing apart into space. And so this idea of a primordial atom, it turns out that pretty much every cosmologist and physicist decided that no, that's not what was going on. But eventually it took a little while to figure that out. And so that was discounted. About the time that was being investigated, and they were realizing it wasn't going to work, Sir Fred Hoyle, a British astrophysicist, looked into the matter, and he thought this was a silly idea. because he said, well, obviously it had fallen into a black hole. And so he started a sort of derogatory term to describe Lemaitre's ideas, called it the Big Bang. And like some big bang happened and blew everything into space. And probably it was Hoyle's opposition to the primordial atom that caused Lemaitre's legitimate work in this matter to suffer a little bit in terms of public opinion. Turns out the idea that the term Big Bang was then applied to what they finally replaced Lemaitre's idea with. And so the term stuck as a way of describing this event, even though originally it was sort of a derogatory way of referring to his fellow astrophysicists' work. Arthur Eddington was able to show, certainly by the 1930s, that this was not going to work. And so he started working through Einstein's equations too, showing that in fact that the equations illustrate that space expands, not that things are blowing apart in space, but that space itself is expanding. And so everything's going along for the ride. And so he proposes an alternate model in which space expands from a very small volume so small that energy is so concentrated you can't get particles. So that alleviates the whole problem of gravity pulling everything into a black hole. There's nothing to pull into the black hole. And so it wasn't until the density of energy dropped to the point you could make particles that gravity started acting, and by that point the universe already expanded beyond that threshold. And so but this high energy concentration would make the early universe like nearly infinitely hot. And so this is often called the hot Big Bang model, distinctly separate from the primordial atom Big Bang model. And it's really unfortunate that they kept the term Big Bang to describe this, because A, it's not big, and B, it's not a bang, and C, it confuses the whole matter as to what you mean when you say Big Bang. Lemaitre eventually comes along. In fact, it didn't take very long at all until he realized that Eddington was dead on correct, and he met with Einstein, worked through the mathematics here, and eventually became a very strong proponent of the hot Big Bang model. So the Hubble Imatra Law. 2018, International Astronomical Union decided that Lemaitre had really been unfavorably or unfairly written out of most textbooks and not given credit for his work. So they voted to rename the Hubble Law as the Hubble Imatra Law. And so the Hubble Imatra Law you get by plotting, again, we talked about this in an earlier lecture, you plot the radial velocity versus the distance, and you end up with this relationship. Now, one thing that turns out to be a little bit complicated is when you plot it simply against distance, you get kind of a weird sort of graph. The problem is the really distant objects, you have to do a little bit of mathematics to properly calculate the distance, because what happens is the measurements are off for a variety of reasons. So if you compensate for that, the line gets much straighter. And so it's the matter of compensating for it that often gives rise to some dispute as to exactly how much compensation you have, which changes the slope of the line a little bit. And so for many, many years, exact value of that slope of the line was kind of difficult to come by. Different people had different values. But V equals HD is what you get by graphing this. This is your y-axis. There's your x-axis. Okay. Just a little bit of algebra, though, says that D equals V over H. So that means if you were to somehow have a galaxy that you could see, and you could measure the velocity by measuring the redshift, then you just divide by the slope of this line, and divide by the slope of the line, and that would give you the distance. And so that's why this is such a powerful tool for measuring distances and and uh, and for realizing that the universe is expanding. And again, it's not things are moving away from each other, it is space expanding. The Doppler shift is not due to things moving away. Rather, the Doppler shift rather is due to things moving away. The redshift in galaxies is not due to things moving, but because space is stretching, which stretches the wavelength. And so it looks like a Doppler shift. Doppler shift is actually a stretched wavelength because things are moving. So that means we have actually different kinds of redshift. We have the cosmological redshift, which is the redshift you get from the expansion of space. That's the light itself stretching. You have the Doppler shift. That's a redshift that's due to things moving. And then you have a gravitational redshift. And that's due to gravity distorting space and time, making light appear redder. So you have three different kinds of redshift right there. And in fact, you even have interstellar reddening, things looking redder because the interstellar medium is absorbing and scattering the blue light. So back when I was in college, I think Astronomy Magazine actually published a short little article, about keeping track of all the different kinds of redshift, because there's multiple kinds of reddening and redshifts that are involved. And so that's what's happening here. Space expanding, and so that gives us an estimate of the age of the universe. Because if your space is expanding, you run the expansion backwards, and that at some point everything was all in one spot. And so that's where Lemaitre got his idea. But this also is a valid way of measuring the age of the universe. So it's an estimate of the age of the universe that assumes the Hubble constant is constant, which we'll talk about that later. But and it assumes that gravity doesn't slow anything down. So again, this is not a perfect measure, but it gives a rough idea of the age of the universe. And so the way you do that is you adjust the units in the Hubble constant, because it's kilometers per second per megaparsec. You rewrite megaparsecs in terms of kilometers, and then take the reciprocal of this 1 over h, doing those unit conversions. That would actually give you a ballpark estimate of the age of the universe.